Hi everyone, welcome to this episode of Keipert Labs. In today's video, we're going to be introducing the concept of stoichiometry, the whole basis of this unit that we're going to be completing. So essentially, stoichiometry is the concept of predicting the amounts of the substances involved in a chemical reaction. That counts for both reactants and products. Okay, so just remember that if we let's take a look at a particular chemical reaction here. Okay, so we have nitrogen gas plus hydrogen gas reacting to form ammonia gas. Now, we will learn a lot more about this particular reaction in our Year 12 course. It's called the Haber process. But essentially what we know is that in this reaction, that the mass of our reactants is going to be equal to the mass of products. Okay, we'll call this the law of conservation of matter, or mass. And the idea being that all the atoms that were there at the start are there at the end, and therefore the total mass of our reactants and products will be identical as long as no particles are lost or gained, the system doesn't lose or gain any particles from outside this process. Okay, and so then that gives us real power to be able to observe how this chemical reaction is going and to be able to then make predictions of how much of each substance that we should have depending on how much we start with, like if we produce how many, certain number of mass of products, what mass of reactants would we have had? If we start with a certain mass of reactants, well, how much product should we make? Okay, that has huge implications for the way that we carry out chemical reactions and what we are able to do as a result. Okay, and so one of the things that I'm going to introduce you to now is a tool we can use in stoichiometry to keep track of the amounts involved, and it's called a before, change, after table. Okay, so what we have here is what we call a before, change, after table, or a BCA table, okay, because BCA. So the way that this can work is that it can help us to keep track of the number of moles of each substance that's present at each stage of the reaction, both at the start, during the change, and then at the end of the reaction. Okay, and so a couple of things that we need to kind of keep in mind here. First of all, we have to start with an equation. Okay, so you have to start with a balanced equation. It's really important that you've got. Sorry, I realised that that's just off your screen. So we start with a balanced equation. Okay, that's really crucial because otherwise, then the process of how we work out how many moles we need at different stages isn't going to work. Okay, and then the other thing that we need to do is that we set up these rows, and then we're basically going to line it up underneath the substances in our reaction as our columns. Now I'm just going to tweak this just a little bit. I'm just going to make it a bit shorter, just so you can see what's happening on your screen, but you don't need to adjust your table. Okay, so the way that we work is let's say that we're going to mix together nitrogen gas and hydrogen gas. Okay, so let's say we start with 3 moles. So now the other thing that I want to identify here is that we only use moles, not mass. Okay, we have to convert everything to moles because each of these substances weighs a different amount. 1 mole of each thing will have a different mass. And so, 10 grams of nitrogen doesn't end up becoming 10 grams of ammonia, but 10 grams of our reactants becomes 10 grams of our products. But so what we end up with is we have to use moles as our conversion process here. Okay, so let's say that we start with 3 moles of nitrogen and 9 moles of hydrogen gas mixed together in a container. So at the start, before reaction has happened, we have 3 moles of this and 9 moles of this. Now, before any reaction has occurred, we don't have any product yet. So one of the key things there is that we always start with 0 product. Okay, so start with 0 products there. All right, now what we're then saying is that during the reaction, that then we can keep track of how the reactants decrease and the products increase. So reactants go down and products increase. Okay, so in this change along, we're going to be talking about how much these go down by and how much this goes up by. Okay, so the idea here is that we are mixing these together so that we will end up with all of our reactants get used up. So we end up with 0 moles of our reactants at the end. Okay, so that means to go from 3 moles here to 0 here, that we have to have a change of 3.0 moles. Same thing over here, we have to decrease by 9 moles. Now the reason that we don't decrease by the same amount comes down to the ratio of the moles here. Okay, so I use up for every 1 mole of nitrogen that I use up 3 moles of hydrogen gas. And so I'm using this up 3 times as fast. I'm going to need 3 times as many moles for that reaction to be balanced and for it to proceed. Now I can also use my mole ratio to work out, all right, how many moles of this will I produce? So what I have here is I've got a ratio for every 1 nitrogen molecule, I have produced 2 ammonia molecules. So if I have, for every mole of this, I produce 2 moles of that. So then for every 3 moles of this that I use up, I'm going to produce 6 moles of ammonia to end up with 6 moles at the end. Okay, now just like we looked at in the previous unit, the idea that these coefficients don't have to add up, the number of moles don't have to add up either. We have 12 moles here, 6 moles here, but remember that the substances we're forming are different. This is a more complex substance that has a higher molar mass than either of these things. So the fact that we end up with a fewer number of moles is not actually that important, okay, because we're forming a different substance. What we do need to be mindful of is keeping track of how much there is, okay, using the mole ratio. Okay, so if I'm just going to do a little bit of working underneath here, the way that I can work out this value here is I know that I have 2 moles of ammonia for every 1 mole of nitrogen gas. So I realize that's the contrast is not so good there. Okay, let's do it here. I have 2 moles of ammonia, a ratio of that for every 1 mole of nitrogen gas. Okay, so then I can use my factor label method to be able to do calculations involving this. Okay, let's have a look at the another kind of practice question on this one. Okay, so let's look at an example of water, what we did with electrolysis, where water is being split into hydrogen gases and oxygen gases. Okay, so I'm going to start with my balanced equation. So I've got H2O as a liquid being broken down into hydrogen gas and oxygen gas. Okay, to make this balanced, I'm going to need 2 of these, forming 2 of those and 1 of those. Okay, and so now I can establish my BCA table. So I'm going to then say, all right, if I start with 50 moles of water, then how many moles of each of these gases I'm going to produce? Okay, so remember I'm talking about moles, I'm not talking about masses. We will start to be able to do conversions involving mass. That will be kind of the next sort of step. But at the moment we're just looking at using the table for moles. Okay, my reactants are going to go down, my products are going to go up because they start from 0. I've produced no product yet, no water has split. Okay, so I'm saying, all right, I'm going to decrease by 50.0 moles to have 0 at the other end. Okay, I'm using up all the water. Okay, and now I'm starting to look at my mole ratios. Okay, for every mole of water that I split, I produce the same number of moles of hydrogen. 2 moles of this I split, I produce 2 here. So if I used up 50 moles here, then I'm producing 50 moles here. Okay, whereas then when I look at this and then I'm saying, all right, well, for every 2 moles of this that I use up, I produce 1 mole of oxygen. Okay, so I've got a 2 to 1 ratio here. So that means instead of producing 50 moles of oxygen, I'm going to produce 25 moles of oxygen to end up with 25 moles at the other end. Okay, so just like before, my moles don't have to add up on left and right hand sides. The number of atoms do, and the masses will add up. The sums of the masses will be the same. But I've got, so 50 moles of this turning into 75 moles of simpler products as it decomposes or breaks apart. Okay, so we can use this type of a table to be able to keep track of how many moles there are at the start and at the end of all the substances in our reaction. Now, in subsequent videos, what we're going to be able to do is take it a step further to be able to start working with masses and then using conversions to moles to be able to identify how much mass we should produce. And also then we're going to see, okay, well, what happens if we don't have exactly the right number of moles of each thing? What happens in the real world if you've got more than enough of one? Okay, and so then we can see, we can use the BCA table in those situations as well. All right, thanks very much for watching. Bye for now.